Okay, today's presentation is on the construction challenges of the Galena Creek Bridge, and I'll talk briefly about the presentation content. First, I'll talk about some learning objectives, a short introduction to long span concrete bridge construction, give a project overview brief of the Galena Creek Bridge and the construction, some common construction issues with long span bridges, use of specialized software, and then a final wrap-up. So our learning objectives for this seminar is to, again, give you a brief introduction to some of the unique issues with complex long-span concrete bridges, more from a construction field engineer's perspective. As mentioned, we'll talk in particular about the Galena Creek Bridge in Nevada. We'll discuss some common construction issues with long-span bridges. And then we'll kind of wrap it at the end with how we can use specialized bridge software like Midas Civil to help construction engineers in the field assist in verifying and making sense of our field observations. So we'll start with an introduction. As we know, the Ashton of God specifications, for complex bridges, we need to look at variation in design parameters with time, as well as specific construction schedules, methods of erection. We need to consider construction methodology, variations in construction schedule and casting sequences, variations in concrete properties, compressive strength, modulus, elasticity, creep and shrinkage, pre-stress losses, structure stability, all forms of construction loading, permanent loads, wind loads, thermal effects, and stress redistribution and deflections. So as an on-site construction field engineer, we typically expect all the previous tasks to be completed and handed by the designers for the engineering reviews. So most times in the field, we take these reviews as being done, complete, and usable for us in the field. So we get a set of documents and manuals that will utilize the erection analysis, the construction sequencing, geometry control, cambering book, temporary works design, stressing manual. We'll make field construction decisions based on very specific contractual specifications and guidelines, best practices, and our experience to help guide us through the project from start to finish. Obviously, we know everything doesn't go as per normal. So when something happens or the contractor is forced to change things due to scheduling or other reasons, then the field staff usually wants to know how those changes are going to affect things. Our typical procedure would be to go back to the engineering reviewers for a guidance. Now, with the introduction of very unique and good specialized bridge software, we can now utilize some of these features very easily in the field if we have access to it. It can give us some more specific insight to the validity of the results that we see in the field. This really helps us bridge the gap between having changes that are proposed, waiting for the answer. This way, with the specialized software, we have an idea as to how those changes will affect the structure before we get information back from the official reviewers. So we'll talk about the Galena Creek Bridge. The designer of the Galena Creek Bridge is the Nevada Department of Transportation. It was completed by a bridge contractor, C.C. Myers from California. As our colleagues mentioned from Microsoft, it's part of the I-580 freeway extension between Reno and Carson City, and the project has many complex bridges on it, Galena Creek being the largest and the most complex. It's actually twin bridges side by side, but as you can see here, it's an 8-mile section of freeway built on the mountainside just west of the 395 highway. The project was started way back in 2004. Due to some contractual issues, there have been 2 contractors actually that have worked on the bridge and the project. So the completion date is now late 2012 this year. Some quick aesthetics and properties of the Galena Creek Bridge. As you can see here, it's obviously a landmark structure built on a hillside going over the Galena Creek and the canyon, spanning the canyon there. It's actually 300 feet off the floor of the creek, so it gives you an idea of the scale of the structure. Superstructure is constant depth box girder, and as you can see, the superstructure and the arch merge together at the crown area. Just another shot, side elevation schematic of what the bridge looks like. Design is to the AASHTO standard spec 16th edition. Low relaxed PT strand, reinforcing steel, high seismic area as you can expect, and California standard design vehicles for overload. Plan and elevation view of the structure, 7-span structure. As I said, twin bridges side by side, which were connected at the arch span and the superstructure for seismic, and also the thrust block locations at piers 2 and 3. And a typical cross section of both bridges gives you an idea of what the side by side view looks like. So segmental aspects are typical for this type of construction: erection analysis, erection sequence manuals, which verify all the forces, the cambers, the temporary works designs, variations in casting sequences, creep and shrinkage per the 1990 FIP model code, geometry control. The structure required very precise, accurate tracking of geometry, which I'll explain later why. So the camber for the arch and the superstructure were developed based on computer models. It also took into account localized deflections. There was some false work supporting the arch construction and the superstructure above the arch. In the field, we also have to account for survey tolerances and casting of the arch. We typically follow the AASHTO guide specs for casting control. Here's a quick shot of the piers, typical rectangular piers founded on drilled shafts. The thrust blocks for the arch span piers founded on rock, competent rock. 37-degree slope. The thrust blocks were poured in 3 separate massive pours, as you can see on your screen here. Arch span, 210-meter span. It was constructed entirely on false work in the second contract, which we'll see a few slides later. Of course, it incorporated the time-dependent analysis for design and construction. The segment lengths casting sequences were varied from the sequence in the plans by the contractor. Geometry monitoring during casting and throughout the entire construction history of the bridge were monitored by the contractor, and also contractor was responsible for stability during construction, as usual. Here is a shot of the arch, southbound arch at completion. You can just see some of the remaining false work being removed. So you can get an idea of the crown area where the superstructure will merge with the arch. Here's a typical drawing of the merged area. Again, constant depth box girder superstructure. There was some transverse post-tensioning in the superstructure. All 3 frame sections of the superstructure. Longitudinal post-tensioning, internal and external were used. There There was also a large number of post-tensioning bars used at the hinge and bearing locations on either side of the superstructure at the arch span. And I'll show you later the hinges and the end diaphragms were very, very congested and required extreme care and geometry control. So some common construction issues of long-span concrete bridges. Concrete mixed properties, construction method, casting sequence, temporary construction loading, age of components, and some other unique circumstances which popped up on this project. Concrete mixed properties. We used aggregate from the site. The contractor proposed concrete mixes from the site and in order to meet the creep and shrinkage requirements and also for reuse of materials. One thing we found early on was that some of the creep and shrinkage tests that were reported by the laboratory it yielded very erroneous results. And literally they did not really know how to conduct the creep and shrinkage tests and present the data. So by using the software, which I'll show you later, it gives the owner an idea or picture what the graph should look like. When I got the graphs for the initial creep and shrinkage tests, it was evident that something was very wrong, and it didn't take long to present some computer graphs based on Midas Civil that basically showed what the creep and shrinkage graphing should look like. So that was one nice use of the software. This construction method was a unique method that was proposed, and it received approval from the Army Corps of Engineers. Basically, the contractor filled in the creek canyon area, as you can see on the right-hand side. They had a concrete culvert which spanned the very narrow creek below, built up a working surface of earthworks which they mined from the north half of the project and utilized for the construction of the arch span. The arch span, as you can see on the left, was built entirely on false work. And here's just another shot of the entire false work and fill setup. The casting method for the arch, it was a hollow concrete box arch rib. The casting method was poured, basically the contractor proposed to pour it in 3 separate pours. The bottom slab, the rib walls, and then the top lid. This was a mock-up that they performed prior to casting the first arch segment. As you can see with the slope, there was some concern that they could achieve the pouring. Schematic the contractor drew up for the concrete pours, basically a symmetrical type pouring from either side of the arch springings. As you can see, the different colors highlight the various lengths and extremities of the bottom slab, the stem walls, and the lid pours. So many different pours. As you can see, I think there was about 35 different pours total. So the casting sequence was quite extensive. Concrete placement in 3 different methods for the arch rib and the superstructure: concrete pump, crane and bucket, tower crane. So just because of the heights and the reaches involved, they had to utilize 3 different methods. Here's a couple of shots of the arch rib. The soffit of the arch rib near the springing off the thrust blocks utilized some integral stair steps, which certainly made it easier for the crew to cast, but also allowed for easy inspection later on inside the arch rib with the steep slope. The lid, you can see on the right-hand side, was finished without any formwork. They perfected the concrete mix and slump and the finishing screed, and was able to cast and pour it without any formwork very successfully. Some temporary loads that were evident on the arch after completion was utilized to drop the formwork and falsework for the arch casting. So these temporary loads had to be analyzed on the structure for stress checks at the various construction stages. After all the lower falsework was removed, then the contractor installed the upper falsework on the completed arch rib in order to cast the superstructure. Again, all the loading had to be analyzed for all construction stages. There was a limitation that no falsework be within 15 meters of the main piers. Typical schematic of superstructure pours, again, quite extensive like the arch rib. I believe there was like 11 different concrete placements, as you can see highlighted by the different colors. All of these were cast in a specific sequence, which is indicated by the numbers. So again, it's quite an extensive breakdown of casting sequences and timing. Here's a shot of the merged area of the arch crown and the superstructure. Again, an integral connection there. The camber of the superstructure in this area was, I would say, tweaked depending on the as-built of the arch. At this point in time, the arch was completed. The piers that would connect the superstructure for the main span were completed, so the contractor had to literally take the as-builts of all three of those things and then kind of come up with the best fit profile for the superstructure. So survey of each of those three elements was very critical in order to determine the like I said, the best fit casting line for the superstructure. As we know, falsework is difficult to model in any circumstance. It certainly was difficult to model with the falsework being utilized to cast a superstructure on the arch. Just off the main piers, 2 and 3, there were some hinges that were to be constructed where there were expansion joints and sliding bearings. The unique thing, other than the congestion you see here, is that the hinge diaphragms and the hinge casting required extreme precision prior to the final casting of the upper and lower hinges where the bearings would sit. One of the reasons for the tight casting requirement is, as you can see, there's a number of steel pipes poking through the rebar there. It's about 35 to 30, I think 38 total. And those were seismic restrainer bars that were going to essentially go from the diaphragms of the main frame of the superstructure to the other side of the hinge bearing to the other frame. And they were about 30 feet in length. And obviously a straight steel pipe needs to be straight through 4 different concrete pours, the end diaphragm, the 2 end diaphragms, and the 2 hinge body pours. So obviously once we were ready to cast the 2 hinges, these pipes essentially had to line up in order to insert the restrainer bars so that we knew the pipe would be straight before and after casting. Deflection control, as I mentioned at the bottom of the slide, was critical to within a few millimeters. That's the tightness that was required to control the geometry at this point. Another unique thing that we found was that because the contract was started very early, of course the foundations and the piers were constructed back in 2004, 2005, is that once the second contractor came on board in 2007, 2008, the columns were very old. They were 4 years old at the time, and being old, the creep behavior was reduced. They were less ductile for superstructure creep. The contractor initially wanted to propose casting, for instance, frame 3, what you see here on the right-hand slide, which has 3 piers and 4 spans. The initial intent was to cast that in 1 pour, but with the age of the piers being, many years old, essentially, if that would have happened, the columns would have cracked. And so to alleviate this, the DOT had to instruct the contractor to institute a closure pour over the middle pier, as you can see in both slides here. Obviously, that wasn't analyzed prior to letting the contract, so it cost a little over $2 million in extra fees. So with essentially a proper analysis beforehand, some of this money or most of it could have been saved, possibly. Another issue that occurred to make matters worse was that Pier 4, which was one of the most critical piers for the southbound structure because of its height and location. In high winds, the reinforcing cage fell over. This area where Galena is built has extremely high winds coming through the canyon, and it's a challenge on most days to deal with. So unfortunately, this incident happened, and the designer was left with no choice but to have the contractor cut the reinforcing cage off at the footing, institute a new column cage, but in order to get the connectivity, they had to construct another smaller footing, as you can see in the right-hand slides, which effectively reduced the height of the column. So the computer modeling that was done had to reflect this column shortening. So how can we use specialized bridge software to help us in the field? Well, there's many ways we can, and I'm going to show you a few of them. So specialist bridge software is typically used in aiding designing and analysis for the construction engineer and the owner. Some other ways to use it, we can, besides handling the large complex structure behaviors and variations that we see in the field, it becomes very versatile to account for many changes, casting sequences, timing, stages that are instituted, delays, any type of unique circumstance that I mentioned before. But this specialist software is really important for pre-stress, post-tension structures where you get a lot of variation in long-term behavior. The project contractor used 2 different time-dependent softwares. Their main program was LARSA 4D. NRV, which was the construction engineer, also used a program called STDS. When the bridge was designed way back in the early part of the decade, BD2 was used from IDS, and the Nevada DOT used SAP 2000 and ADINA. As you can see, there's many different packages. Obviously, each of those packages yield different modeling results, and each has their own uniqueness and features. It becomes very difficult to replicate models, especially a structure like Galena. So what happened was that this led to some disagreements in the analysis results, and the differences were really in the geometry and the cambering. As I mentioned before, for this particular type of bridge, this was the most critical aspect during construction. So what I did was I developed some comparison models using Midas Civil to help confirm what we were actually seeing in the field in light of the differences between the LARSA and the SAP models. So I developed a number of two-dimensional longitudinal models, some very simple models and then got into some more complex models. The simple models had less construction stages, single element pores, group tendons, whereas the complex models had a larger amount of construction stages to model the exact casting and sequencing that the contractor used in the field. The element pores were broken down into 2- and 3-part sections as the contractor had done the actual casting. Individual tendon profiles were modeled instead of group tendon profiles, as you can graphically see on the left-hand slide. The upper arch false work was modeled and the assumptions noted for that, and of course the concrete compressive strength, creep and shrinkages per the CEB 1990 code. So overall, I developed about 20 different models with some simple, as I mentioned, some complex. Again, varying the stages, the tendon groupings, going to individual tendons, breaking down the element pores of the superstructure and the arch rib to match what we were seeing in the field. The initial models I assembled basically matching the contractor's initial model that he had used in the erection analysis and cambers. However, as construction progressed, it really became evident that because of the type of structure and the size of it, the uniqueness and geometry control required, that a more complex model was needed. It really allows the most flexibility later when the contractor starts to vary construction schedules. Obviously, we have the 4 seasons where this bridge was constructed, so a lot of things played into the contractor's schedule. So a more extensive model was certainly the way to go with this, rather than a simplistic model that was developed early on. So the MIDA civil models that I used, the construction stages I simulated and updated with the actual sequencing and placement on site. The elements, the arch rib, the superstructures were all modeled in 1-, 2-, or 3-part sections, tapered composite sections with elastic rigid links connecting the arch and superstructure nodes in the merged area. I used the individual tendon profiles and stressing sequence that was actually proposed on site. Accounted for the temporary loads, the strand jacks, the exact weights that were utilized for each of these equipments, and then simulated the false work component weights on the arch rib utilizing lumped weights for formwork, false work, beams, posts, and cable bracing. Here's some typical model slides. As you can see, with the upper diagram is the completed model structure, and then you get to see the arch rib construction, the merged area, and the many different pores of the superstructure in the middle slide. So here's the one of the main piers, pier number 2, with the arch span to the right-hand side. As you can see in the upper left, the beam end hinge release is where the expansion joint and bearing will go between the frame to the left of the hinge and the frame to the right. False work is modeled. The loading of the false work is modeled using compression-only elements. Cable bracing was installed to simulate the California type cable bracing for false work design. Elastic links connecting the false work nodes to the superstructure nodes. Tapered composite sections used throughout, and simulated formwork springs to give the model some rigidity during the casting. And again, the other side showing false work supports near the main pier number 3. You can see the individual tendon profiles, profile tendon points were constructed as per the actual profiles used on the shop drawings. And as I mentioned, there was a lot of models, a lot of sensitivity analysis were run to see how varying the casting sequences, varying stressing sequences, false work removal, variations. So many different models could be run to verify what the contractor wanted to do. It got to a point during construction where he was, because of some cambering issues, that he was really playing with the sequencing to try to find out what the best sequence was for false work removal in order to get these two sides of the hinges to line up in order to cast the final cores there where the beam end release is located. So as I mentioned before, the concrete properties, the creep and shrinkage graphs we got from the lab, you probably wouldn't have believed your eyes what it looked like. It was completely evident that it was incorrect. By using Midas Civil, what you can do is very quickly show the owner what the graph should look like. I didn't actually use the actual concrete properties, the actual creep and shrinkage results we got from the lab once they reported the data in the correct format. I just basically used the material properties as per the design in order to run the Midas Civil models. Midas Civil, obviously, we needed to do some checks and balances to make sure that the model was matching reality. So there were a number of different checks that I did for false work loading, just to confirm that that the false work pipes were completely in compression and not in tension at any time, and checking bending moments visually just to see that everything was looking normal. As I mentioned, it was a very complex model, so at a number of different stages, you want to basically double check your modeling by doing a reality check, essentially. Tendons, as I mentioned, I went from group tendons initially to modeling each tendon specifically, and one of the reasons I did that is typically for any tendon profile, we have a center of gravity profile on the post-tensioning shop drawings. And as we know, most specifications require that that the elongations that we read in the field be within an accepted plus or minus 5%. Some states is plus or minus 7%. Midas Civil, with the complex model, it allows you to model each tendon with the stressing sequence and timing that we actually used. And what I found was that by modeling the individual tendon profiles, it compared better to the actual elongations viewed than just using a single center of gravity profile. Why is that useful? Well, it's useful because, as I mentioned, the elongation control, you want to keep it within the plus or minus 5%. If it doesn't, then obviously the design engineer has to get involved in order to confirm that he's going to accept the stressing results. If he doesn't, then we end up doing dead-end liftoffs. We may end up, if we do dead-end liftoffs, which is a very dangerous item, there's a chance that you can break strands or wires. There's a huge safety issue. we ended up doing this on the southbound bridge frame 3, and we ended up breaking some wires. And the reason why we did was because that a single center of gravity profile was used, and some of our elongations varied up to 20% from the theoretical. So as you can see, it was a huge difference. These tendons are 240 meters long. They're draped in several spots with a very unique profile. So by using Midas Civil and modeling each individual tendon in the sequence that it was stressed, this variation would have been evident, and it led to a more practical reasoning as to why we were seeing the huge 20% difference. By knowing that reason, by knowing that we were going to see that difference, we may not have done the liftoff and compromised the safety of the workers that had to do it. Obviously, when you lift off and re-stress, you can, depending on where the jack grips the strand, you can, like I said, break wires or strand. This structure was so sensitive that we could not afford to lose more than one strand. If that would have happened, then we would have ended up de-stressing many tendons in order to get what the designer needed. So that would have cost, again, a lot of time and money, besides being a dangerous operation. So again, Midas Civil with individual profiles, it showed that extreme difference, and it would have allowed much more easy reasoning as to why we're seeing the different elongations. Here's a screenshot of Midas, the printout in one of my complex models, and what I found with the elongation variation is that the Midas Civil readings were upwards of 5% closer than using the single center of gravity profile. Well, 5%, as I mentioned, it's kind of our limit before we kick the results back to the designer. So, so what you can see from this is that it may end up saving you from doing a lot of extra work and saving time with the elongation reviews. The tendon force loss, as you can see here in the screenshots, we found that with the tendon liftoffs we had to do for frame 3, we found that the Midas Civil model was 2%, upwards of 2% closer than the actual liftoffs predicted using a single center of gravity profile. So again, you can kind of get an idea of the accuracy that the model has using individual tendons versus a single center of gravity profile. Obviously, the bottom part of the slide, easy calculation of tendon weights to confirm for payment purposes. Geometry control was, as I mentioned, the most important thing of this structure. The thrust blocks with the 37-degree incline on the competent rock were monitored for settlement rotation. The top of the tall piers above the arch span were monitored for translation. False work pad settlement monitored on the fill. The earthen fill below the arch during arch construction. Arch rib control points monitored during each construction phase. The next slide, I'll show you how they did that. As I mentioned, the central frame above the arched and emerged area, again, they took the as-builts of the 2 main piers plus the arch as-built in order to fine-tune the superstructure casting line. Casting tolerances within plus or minus a 1/4 inch, 7 millimeters. The contractor with the twin bridges used the same model for both bridges. The pier heights were different for both bridges. Only a few of the piers were of different heights. Later in the presentation, I'll kind of show you what differences Midas Civil was able to pull out using models for each of the north and southbound bridges rather than just using one model. Here's a quick shot of the survey targets that monitor the arch. It was an automated survey, so very high tech. Survey targets epoxy to the arch rib, and basically this instrument could survey this arch in literally a matter of seconds and get a correlation for all the targets. So very, very high tech. About $60,000 worth of equipment was used to confirm the arch rib survey. Arch camber. What we found in the field versus using the Midas Civil models, and again with such a long span and varying temperatures and survey times, the contractor tried to survey this before sunrise, but sometimes it just wasn't possible. So what we found with the Midas Civil model, that at various critical construction stages, the actual survey compared reasonably well to the Midas Civil, within 5 to 15%. Keep in mind that the actual structure was more stiff due to rebar, which wasn't utilized in the model. Temperature changes of the arch, as I mentioned, with the different survey times, which made it impractical to survey before sunrise each time. The contractor had to account for that, and so what I did with the Midas Civil in the bottom slide is instituted a set 20-degree Fahrenheit temperature load, and compared it with some actual data in the field. And as you can see up top, it modeled itself very well, only a few millimeters different at times. So again, that was a nice feature that you can use Midas Civil for to confirm a unique stage of construction. Superstructure cambers, as I mentioned, were dictated by the arch crown and the piers. Deflections, as I mentioned, was slightly less than predicted due to rebar confinement and by not using the actual concrete properties. Pier deflection. It was significant in this project, and the reason why is that as you can see with the graphic in the center, some of the pier, the horizontal movements of the piers is upwards of 4 to 5 inches, piers 2 and 3, inwards. And these piers were cast without any horizontal cambering. They were survey monitored with targets on top of the pier. One of the reasons why this is important to know in the field is that if you look at the bottom statement in red, if we ended up sending a surveyor out and he said that the pier is 3 inches at one construction stage from plumb, you can imagine what delays would happen. So by modeling the structure as accurately and as detailed as you can, it allowed a DOT owner to get an idea that yes, something unique was going to happen with the structure, and more so than any other structure. Typically, if a pier is surveyed on most projects, if it's within a few millimeters, everybody is fine. If you survey a pier and it's 4 inches out, people will really start to wonder what's going on. One of the reasons it was important here is that the thrust blocks we were monitoring as well for rotation and settlement. So if we didn't know what the piers were predicted to do horizontally, then we would have assumed that the thrust blocks were moving. So by knowing this, using a model with like Midas Civil, we were able to get a better understanding as to what was going to happen during construction at the various construction stages. We're going to go back to the hinges. This is the superstructure hinges that I mentioned before, and the locations are shown on the bottom. So as you can see on the top schematic, the geometry control for casting the central portions of the upper and lower hinge where the bearing sits, as you can see, it requires a high degree of geometry control. And essentially, as I mentioned before, the seismic restrainer pipes were going to go through the two end diaphragms plus the two hinge bodies. Obviously, a straight pipe, the geometry essentially needs to line up at the time you're casting the upper and lower hinge, critical within a few millimeters. The hinge curl was predicted, and you can see the varying prediction, 1 to 6 inches, depending on how you modeled the structure. And this is where the owner and the contractor's engineer had some disagreements. The hinges are very sensitive to creep, shrinkage, column stiffness. The amount of curl is mainly affected by the speed of casting the frame 2 superstructure. And as I mentioned, the alignment of the hinges is critical for the installation of the seismic restrainer bars, the deck concrete the rebar placement, expansion joint installation, and rideability. We found that the Midas Civil models that I developed and the DOT SAP models were more accurate than the contractor's models. Now, contractually, the contractor used his cambering values, and his cambers were more between the upper and lower hinges, and what that would lead to would be a polymer overlay just because of the rideability issues. Here's the breakdown of the hinge 1 and 2 cambers. So as I mentioned, at the time of casting the hinge bodies, the two end diaphragms on either side have to line up. Again, this is the contractor's responsibility. Since they did not line up at the time of casting, the contractor varied the false work release on the arch after the hinges was cast. So again, the contractor had to play with his construction sequence and therefore his modeling in order to kind of fit his actual cambers and deflections at the time. Once the hinges were casted, all the post-tensioning bars, everything was stressed up. The Midas Civil models that I developed, the load transfer deflection at the hinges was approximately 1 inch, slightly less than 1 inch. With the 4 hinges for the northbound and southbound bridges on either side of the arch span, the actual hinge deflections at load transfer was between 1 to 2 inches. There was some variance because of survey times and the slightly different casting sequences between the north and southbound bridges. So overall, the prediction was for Midas Civil was fairly close to actual, keeping in mind of the survey time issues. So for summary, let's look at what I wanted to do also with the Midas Civil model was typically we run a time-dependent model to 30 years or 10,000 days. What I did was I ran it about 150 years, and the reason I did was because this particular bridge had no built-in adjustments for geometry after it was completed. There were no future tendons. There was no way to correct the geometry after it was done. So what I did was basically ran a 30-year model and compared it to a 150 to 50-year model, and the difference is after load transfer were virtually negligible. As you can see in the bottom chart, very little difference. 10 to 15 millimeters. The northbound and southbound bridges, as I mentioned, the contractor used a single model. With the varying pier heights, what I did was double check the pier movements, and certainly Pier 4, as I mentioned, for pier deflections there on the right-hand side. The pier movements for that particular one differed by about 11 millimeters from its southbound counterpart. So again, you can use the different modelings for twin bridges if they're not the same geometry or layout, to just double check. Very simple to do with just varying the pier heights. I'm going to wrap up some final thoughts. Obviously, specialized bridge software can be used for a number of checks by the construction field engineer. It was very useful in this particular instance for camber control, deflection monitoring, modeling of false work and temporary loads, and tendon stressing. It allowed us to reason through what we were seeing in the field, so we could have a better understanding of what was predicted and what was to be expected. Again, going back to the pier deflections, the tendon elongations, the cambering differences with the varying construction stages. The reasons noted the differences between the model and the actual structure. Again, the rebar wasn't modeled, which makes it more stiff. You can utilize the actual concrete properties from the creep and shrinkage and strength tests versus using the model codes in the software. Temporary construction loads are difficult to really accurately predict. You're kind of using best guess values. Again, with this structure and its location, there is significant temperature fluctuations. You also have in the field placement issues, errors related to duct profiles, survey, and then if you get into 2D and 3D model assumptions. Here's a shot close to finish. Both of the bridges are now finished. All of the false work is released. This is not quite an updated picture, but it's pretty close. So it gives you an idea of the size of the structure. Again, keep in mind that the height of the crown of the main span and the arch is 300 feet above the creek, so it just gives you an idea of the size of this bridge. As our colleagues from Midasoft said, any questions, if you could just email them to me or email them to Midasoft, I'd be happy to answer any questions on the modeling or the structure itself. And, thank you very much for your attention.
All right, thank you, Hilary, for your amazing presentation, and I hope everybody enjoyed that. As he mentioned, please send your question to midasoft@midasuser.com or to the Hilard's email. Thank you, everybody, and you have a great evening.